Hello, everyone. The objective today, if you've been following along, so we're still going to use the same use case because I think that's very easy to kind of follow along. So we're still going to be looking at that Kaggle house price dating set we started looking at on Monday, and it's the same one that's in our prerequisites as well, such as data literacy. So what we want to do is something fairly basic but quite essential. Like every real estate company out there, if you ever go onto these websites, predict the price of your neighbor's house or your house or something like that. How do they do that, right? Zillow started a service about a couple of years ago where if you put your house, if you're lucky enough to own a house, you put your house into their system, it gave you a price prediction. They would actually take that price and give you a contract to buy your house off that. I thought that was very ballsy. Like I thought that was crazy. Well done them. And then they pulled it a year later because they were losing money. so, so this is why doing good prediction is so important. But it was a great model because we have folks from Zillow present at ODSC from time to time, and it is a great team there. So, but the problem with house price prediction, you guys saw what happened to the stock market, interest rates, and all that stuff. Whiplash left and right. House prices are, as we stay in financial markets, stocks go up like an escalator. You see here, this is the escalator. They go up, price go up, and then they go down like an elevator. Whoop, whoop. And trust me, that elevator can be minutes, seconds, not even hours. So, and of course, you can extrapolate this property sales prediction to many other use cases, right? Anywhere we have similar kind of tabular data, we have a similar feature or set of target features you want to do. And, just so people don't get lost, kind of the first course in this series was like data literacy. This was on demand. It's available in your bundle to view yourself. I do refer back to it now and again. So I've learned my lesson. I've added it here. And then we had machine learning data prep Tuesday. Time flies when you're having fun. We talked about one hot encoding and stuff like that. And again, like it's okay if you're not, you're still not too comfortable with that. You have time to review. And what else we have here? Yeah, last week we did our introduction to AI and machine learning modeling. And I will go over that a little bit because now we're going to encode all of these things we talked about. So let me not get ahead of myself, though. Let's see what's on my slides first before I kind of get into the weeds there. All right, we got 3 notebooks we want to look at today. They get more complicated as time goes on. So lesson 1, we're going to look at that machine learning, data science, classical workflow. And again, when you get to a job, this is most of the work you're going to be doing is the kind of work that's in notebook 1. Data profiling, figuring out your features, correlations, visualizations. Then we get into feature engineering and coding, transformation, and then code 3 is a little more advanced, various types of linear models, decision trees, and clustering. But again, if you're kind of getting lost in the notebook itself, number 1, the notebooks are quite verbose. And also, again, go back and look at these 3 courses, the data literacy one, the introduction to AI one, and the machine learning data prep, because I try and, of course, repetition helps reinforce your muscle memory, but also we don't have time to start from scratch every single time. So I do a little bit of overlap, but not as much as I would like to, just to keep everyone in the same level, the same pace. So if you feel like it's the code's a little heavy going, don't worry, don't panic. And the other thing as well, it's kind of like classic math. Even though AI is advancing at a massive pace, this stuff is quite evergreen, right? Because AI is just like classical math. One builds on top of the other. So I don't think this to go out of style. So take your time and learn it. It's not going to go anywhere. All right. So those are notebooks. And as mentioned, the objective is to predict the sales price. And this is a pretty serious thing. Like if like Zillow, like it's one thing to be a broker and say, I'm going to predict the sales price. Yeah, I think the house will sell between $500,000 and $600,000. What if you were Zillow and your boss says, we're going to make an offer based on your price. not plus or minus 5% or 10% on that actual price. And this actually did happen. So this is not, I would say, a toy example. This is a real world example. Maybe we don't have enough data to really make that accurate position, but we are on the right track. So we're going to do some data profiling, refamiliarize ourselves with that data set we used on Tuesday. We're going to do some data cleaning because remember, any missing values and things like that, that will affect our model. Look at outliers. Maybe we keep the outliers. Outliers are values that deviate from the norm. And what is the norm? As we'll see later, they're clustered around this regression line. So we'll look at outliers, stuff that are abnormal in some respect. And then we'll do some feature engineering. We already talked about one-hot encoding, but I'll go over that again real quickly. Because remember, machine learnings, they want non-numerical or categorical variables as we work with a lot. And in this data set, not always are non-numerical variables in a numerical format. Then we want to normalize. We want to normalize that data. We had some good questions around that last week. And then we also want to do some feature selection. And how do we select the best features? So we covered that a little bit when we looked at our correlation matrix on Tuesday. And then I think we touched upon creating new features, right? So recall in last week in AI training, we talked about training sets and test sets. Very, very common. We talked a little bit about cross-validation as well, where, well, what happens if some of the data is 20? So let me slow down a second. So where did we cover this? We covered this in data and, no, which one did we cover this in? I sometimes have trouble remembering myself. We covered this in this course here. So I think it was around, covered that visualization. It's in here somewhere. I know it's in here somewhere. I'll explain it. I recall what we did there. So when you want to figure out how accurate your model is, there's a very, very simple trick. So let's say you have 1,000 rows of data and 80 potential features or columns. What you can do is you can hold back 80% of those rows. Let's call it 800 rows. And you build your model based on those 800 rows. And then you take your model once it's built, and using the 200 rows you haven't shown it, you basically said, go through each of those 200 rows, and for each row, make a sales price prediction. And then I'm going to measure the difference between the sales price prediction and the actual value. So let's say I predicted a price of 500,000 and the actual value was 480. Then whatever that had a 10% error rate or 5%, whatever it is, 5% error rate, right? And then you add all those up and you average them out. Or you do a square root, mean square root or something like that. We'll look at some error ratios there. And that's cool, right? That's very important. But cross-validation is even better, because what you're doing is, well, what happens if you had more outliers in this 20% than you had here, right? It's not going to perform very well. So what you do in cross-validation is mix and match the set. So on the first run, this will be 800 rows, the first 800 rows, and this will be the last 200 rows. And in the second run, I'm going to take I'm going to go from row 201 to row 1000, and I'm going to use my test set from row 1 to 200, and you mix it all up. So that way you reduce the chances that you're overfitting the model, or just some randomness in how you selected the data set is influencing the results of the model, and that gives you a more accurate result. So we'll do some cross-validation. And for model selection, there's lots of different models you can use, and which model to use when. I think we went over that in Gen AI literacy. We went over that in our AI introduction to AI, and it is kind of nuanced. There are tools for help, like some of the tools are just brute force, or not so brute force. Now they understand it's tabular data. They can look at the data and do this kind of like auto machine learning, and say, well, okay, this looks like linear data. We'll use linear regression, and we'll try XGBoost. Or this is a set of images, so we'll use deep learning or something like that. Um, but but which models is more of a nuanced topic. However, we will be looking at this famous library. We've had many of the contributors, the core contributors like Andy Mueller and Thomas Finn and other folks, and Guillaume from France, who's still active in scikit-learn, I believe, come to ODSC. So it's a model. It's been around 15 years, I think, maybe a little longer. Great library, still massively useful, still my kind of go-to. So we'll learn about that library, and then we're going to train the model. And one of the things we skipped last week, we talked about hyperparameter tuning. And these are parameters, like almost like arguments you give into the function of the model. So we talked a little bit about that. We're going to cover that more. And then we'll do some model evaluation, because how do you know if your model is performant or your loss function is the lowest possible value? So yeah, we're not going to cover machine learning operations like ML ops or LLM ops. It's amazing how easy that's become. Doesn't mean it's easy at production, but there's lots of tools out there for doing LLM ops. And then if you attend ODSC, there'll be lots of talks around that. But that's something you worry more about when you get to, once you have a job and then you have to deploy it. And you have to kind of, for a lot of data, it's depending on how the company, what their policies on deployment and how they do it and what their infrastructure and stack is. All right, scikit-learn library, very popular because it's so easy to use, wide range of algorithms. So pretty much most of this data science and machine learning algorithms are included in scikit-learn. And we'll also, on Tuesday, we looked at pandas and a little bit of NumPy. NumPy is basically a numerical Python library. And matplotlib and Seaborn, we actually looked at these two on Tuesday. Just a refresher on feature engineering. So remember, we talked about this before. You can go look at your, if you look in this directory here, you will have this, let me get you a link to this. You see this Kaggle datasets. That is the one we're using. And it has 1,460 rows or 61 and 81 columns. And now the columns, you can think about it as features. One of those columns is a very special column called the target feature. And the rest are features that may or may not impact the price, right? So you have your raw data, you figure out which ones are your features, then you do your modeling, and then you give your insights, right? So this is your source here. And here's a quick slide on feature selection. We'll talk about these again: normalization, standardization, one-hot encoding, binning, log transforms, and all that good stuff. Again, if you go back to here, this is my this is our course we covered, guys. On this is the course we covered on. Sorry, which slide am I in here? This is the, here we go, yeah. So again, go back to these slides if you're not familiar with feature selection. So we talked about inner data set, and this is the exact same data set. How do we figure out features like number of trees in the yard may not be significant at all, and why bother with it? Whereas number of bedrooms and number of bathrooms is going to be heavily influenced in that. And we talked about feature selection. We also looked at the target feature here, sales price, which is different from these. And if you remember your statistics, these are the independent variables. Well, they're actually not quite independent. There is some interdependencies, but for this purposes, these variables are independent, and this is your dependent variable. So when these change, like if the number of bathrooms shot up from 2 to 7, the sales price will have an effect. Generally, it will go up, right? And we also looked at supervised learning. So the target feature here in this case is the sales price. So that's how we know that. And then we had our house data and our learning model. And then we looked at feature selection. So for example, we want to know how correlated or how strong the relationship between the target feature, sales price, and another feature. Here we're looking at the size of the house versus the price, and you can see as the size goes up. And because we're trying to do it here is like part of feature selection is we have 81 rows, but can we drop some of those? Because again, you could be dealing with much larger data sets, and dropping the features that have no impact or meaningless, stuff like that. So oh yeah, here's training and test. We talked about that here again. So if you're unfamiliar with the training and test, go check that out. Another thing we should talk a little bit about, which can get confusing, is normalization and standardization. So again, it helps if you go back to if you remember your statistics, awesome. You probably know more about statistics than I do. But if you don't, if you're a little bit rusty on it, do take our prerequisites on statistics. Don't worry, it's only a couple of hours. Actually, no, I think it's 90 minutes. It's not that big, thick statistics book you had at college or still have. But let's go over really quickly a couple of key facts here, because in machine learning, and again, a reason why machine learning engineers and data scientists spend so long working with the data, even though if the data looks very clean in tabular format. Let's look at our data here again. Even though it looks very clean, like this looks like a great set of data, there's no missing values. I don't have any, let's just assume it looks good. I already see some problems with it. But let's see, it's a good looking data set, right? Machines think differently. And what they're looking for is all kinds of nuances. And once you start to understand data, and like my favorite person I like to hire as a machine learning engineer or a data scientist to train them to become a machine learning engineer is a data analyst, because they're so used to working with data and they understand the nuances of data and they take their time. Whereas when a coder comes to machine learning, all they want to do is code. They don't take the time to look at the data. So apologies for all you code first folks out there, but I know your tricks. They tend to just rush into the code and everything can be solved by code. No, it's taking time to profile and understand the data is very important. So think about standardization, think about standardization, right? So in statistics, that's like you want the standard normal. You want that beautiful little bell curve. And if you remember, we standardized around the mean being 0, and we have a standard deviation of 1. And there's a nice little trick you can do is you can take a data set that's not standard normal and you can apply standardization or z-scoring, which a lot of people call it that. And that's many different names for us, Gaussian normal distribution, your various distributions. And that's important because, again, machine learning, data science, you have to, and again, we're not going to get into too much detail, but you kind of, if you understand the data and you understand the model you want to use. So if you want to use linear regression, which we looked at on Tuesday, if you want to use K nearest neighbor, which we looked at last week, or you want to use some more pretty traditional things like support vector machines, those models perform better when your data is standardized, right? So it's, again, mean of 0 and standard deviation of 1. Then you have normalization, which I use a lot. Maybe I overuse it. But let's say you're dealing with, I don't know, something like you're dealing with commercial real estate, and a building might have, 500,000 square feet. And then you're dealing with, I don't know, number of elevators in the building, 3, 4, 5. Like, there can be a bit of imbalances just in the scale of those. And I'm not saying that's actually a problem per se, modeling real estate, but just giving an example, you got the scaling problem. So say you want to just bring that down to a fixed range, because as we looked at on Tuesday, if you normalize it and bring it down to a fixed range between, there's various types of normalization, but one of the most common ones we use is min-max. So here I show it between, actually, no. Yeah, -1 to +1. Yeah, -1 to +1 is the most common normalization teeth there. And that's when you want to kind of bound the values within a range, and common for when we do stuff around neural networks. And I use it for other stuff as well. I think I kind of overuse it. And you'll find out as you get to notice, like some of these techniques are sensitive to outliers, some are not. Like we'll see some house price normalize house prices. We may want to keep them. We may not. So we can talk a little bit more about that later. And then it's also good to understand your data types as well. So I know a lot of us skipped over this, but if you did not take a look at data types, you may want to look at that. Where is this? Yeah, we looked at various data types, because another thing you want to understand is continuous versus discrete. So some of you have taken this continuous math, some of you have taken discrete math, but think of usually when you measure something as continuous, like you can say, well, your height may not seem like it's continuous, but yeah, you can measure your height to a very minuscule scale. But discrete would be the number of siblings you have. You can't have half a sibling, right? So understanding what variable is continuous and discrete kind of gets important in machine learning at this stage, because you want to, generally speaking, but not always, you want to standardize continuous variables and normalize. Well, you can actually do both. But if it's already a discrete integer, you may not want to do anything with it, right? But if it's continuous, you definitely want to standardize. If it's discrete, you either leave it alone or standardize it. If it's categorical, which we have a lot, then we're going to use something else. We're going to just do one-hot encoding. And when you do one-hot encoding, you don't have to scale or normalize it. Yeah, and that's it. And then the last thing is, generally speaking, you do not normalize or scale your predicted value, because that's the thing you're trying to predict when you go into model. Sometimes you can do the log transform of say something like a sales price to help you build a model, but then you got to transform it back to do an actual prediction, because otherwise your predictions could be off. All right, so I know I went into that a lot, but having given this boot camp before, the notebooks are pretty dense. So I'm more concerned that you're following along and I'm not losing you in the terminology rather than notebooks, because you can go back and look at the notebooks and run the notebooks at any time you want. And here's cross-validation. I always forget what's in these slides. So see here, we got the training set, test set. So see, imagine the training set is just that rectangle there, that linear set of data with lots of little rows in there and all that. You can see that it moves along. By doing a fourfold, you're not going to miss any data there. So again, and by the way, that's a parameter. That's a hyperparameter tuning. That's a parameter that you can tune. So is it 4? Is it 5? We'll go back and look at that, and I'll cover decision trees once we get to that. So let me see. Let's get to the notebooks. So you guys like it when I share the notebooks with you. So let me get you the first notebook. So I got to reconnect here. So this is the first notebook. And again, you can grab it from the chats. And as always, I got to zoom in here, right? So let me know if this is clear. So let me clear out my output so I can run the code. And again, don't feel like you have to run the code with me. Okay, let's start from scratch here. So again, I'm going to go through this notebook pretty quickly because we covered a lot of this on Tuesday and it should be pretty fresh in your mind. So again, we're using we're collecting this data from the using wget, which is kind of like an API. It's same data set as you have here, this one here, and We'll do our, now that we see it's loaded, wget here, I can tell it's loaded because it's telling me the number of the data set side here. It's okay. And then as we talked about a lot of times before, we're doing our data profiling. And to do our data profiling, we're going to use our favorite library again, which is pandas, import pandas. We're reading in that CSV file that's in memory right now. And we're asking it the shape of the data. And very importantly, as we talked about data types, understanding what, because again, we're going to start prepping the data, what data types we have. So we see we've got some floats in here, a lot of objects, which we know from looking at the data are non-numerical categorical variables. These are, we have some integers in here as well. We have some more floats. So pretty standard data set, right? So you'll be happy to know I did this last year for this course. It took me quite a while. I think I was using ChatGPT 3 at the time. It wasn't that good, but I got through it. I definitely have lit. So what I did was, what's very important as well, you find in machine learning, domain expertise are so important, right? So it doesn't matter if you're working in tech, generic tech, or healthcare, nonprofit, government, real estate, finance. They all have their own domains, and understanding that domain is very, very important. So what I'm trying to understand is this is kind of like the domain-specific real estate code. I have no idea of what, for example, which is some esoteric ones here. Yeah, mass, mass, I have no idea what this means. But I guess what it means is mass veneer, right? You know, you put a veneer on the house. It's pretty common in some areas of the US to have veneering. So vanasse is type of masonry used. Does that have an effect on house price? I have no idea. We're going to find out. Most sold, months sold. So some pretty weird stuff in here. Some of it's kind of like if you've been in the US a while, you kind of get it. If you're, not from the US or, not familiar with real estate, some of these will be quite baffling. So anyway, understand your data set. 3S, and yeah, like you see down south especially, they have these beautiful wraparound porches, sorry, not the car, wraparound porches. And I think sometimes they're screened in or they have windows you can open up, meaning basically it means it's not heated. So you can use it spring, summer, fall, but you can't use it in winter. But I'm sure some people do. Anyway, so know your data. And then we get into here is some descriptive statistics. And again, one of my favorite things to do is like and this is why I, love pandas and code, because I can do something like this. And it will take the numerical features. And again, we haven't done feature selection yet, but it'll take the numerical features. And again, this backslash means here that it's kind of skipped some of them. But here we're looking at the lot frontage, lot area, and it's telling you the mean, the standard deviation, the min, the max, and the various quartiles, right? So again, when you're thinking about normalization, scaling, this is where your mind starts to think, okay, what am I going to do with this data, right? Lot frontage, min, max. I have some missing values here. I'm trying to look for something with min and max, kind of high min and max. Lot area, that's, standard deviation is quite high there. That's 10,000 square feet or whatever. We got a 1,300 lot, which is quite small, to a, wow, that is a big lot. That may even be an outlier, right? Overall quality, I can see this is scale between 1 and 10 because I got a min of 1 and 1 and 10. So right away, you should start to think about, once you profile the data and use that to scribe, don't just skip through that. Start to look at the data and say, okay, what is this data telling me? Missing values, what kind of scaling do I have in here? And then of course, we need to move on to, and sorry, I'm skipping through some of this code here. Yeah, so you just use the scribe method like before. Get numerical statistics. And of course, we have non-numerical data for this real estate data set. Most of it's categorical features. Doesn't necessarily have to be. So what we're going to do here is we are going to look, we're only going to describe of type object. So see here, the include equals object. So that gets rid of, not gets rid of, but it excludes the, for this data frame. Remember, we talked about how to create data frames. For this data frame here, this new one we created, this is a sub data frame of this one here. And we have this new data set here. So what do we have here? These are our non-numerical variables. And now instead of giving us the mean, it gives us unique, top, and frequency. So for zoning, we've got 5 unique values, very important. The top one is RL, and that occurs 1,551. So you can see right now, I don't know what RL means. Again, I assume it means residential. So this is a good data set for predicting residential, but not for non-residential or mixed use or something like that. And we also got either different types or whatever. So again, data profiling, look at the data and say, if it's not residential, should it be in the data set, right? This is paved or not paved, I guess. And yeah, lots of interesting information here, which I won't go into in too much detail because we'll see the correlation. But study this data set yourself. And if you have the time, go through them one by one. And because again, if you had, you'll hear a term high dimensional data. High dimensional data usually means, lots of given columns. It can also mean like, remember when we did it on Tuesday, if we have 5 unique values in a categorical, we'll take that one feature and create 5 features from that one feature. So imagine we had, like in text, if a paragraph of text, there's 150 words in that paragraph, kind of a long paragraph. But in that paragraph, there's actually 150 features. So that's why when people are talking about text, the dimensionality is just massive. It goes into the millions and billions. But it's okay to start small and understand it. So check that out. And then I think here we're just reviewing unique values. So kind of like what we're looking at here, unique, but just better thing here. So ID obviously has 1,460 unique values. That's a feature we would drop from our data set because maybe for looking up a house we might need it, but for modeling, what do I need that? I don't need that. And then you can see here, like I wouldn't want to convert this to a categorical feature. Otherwise, I would have 1,000. I would add 1,073 features to the one we already have. But luckily, I think that's a numerical value anyway. So same as year built. So anyway, that's our profiling. And now, of course, we're doing what we did last week. So again, we're just using unique and sortify, and we're only doing unique on numerical values there. Sorry, no, that's not it. Number of unique values in each column. And then here, what we're trying to do is look for null and missing values again. So did that last Tuesday, pretty common. So again, we're looking at the house data frame, saying is null and finding out which ones are null, and then sorting false. And then if it's greater than 0, printing those out. So we've got a bunch of missing values here, which we looked at last time. And I kind of go into some details there. So we talked about this in our data literacy. So it's kind of your choice whether to keep the missing values, drop the features that have too many missing values, or extrapolate and put in the mode and the average. We looked at that on Tuesday. So that's something we covered on with our machine learning data prep, missing values. One feature we need to look at very closely is our target feature, because we don't want any missing values there, and I don't think we have, because apart from the one header row, we have 1,460, and again, it's telling us a lot of information here, because we see the mean price is 180,000 and the max is 755,000 and the minimum is 34,000. So I can tell straight away this is kind of an old house data set, because in the US, for most parts of the US, and I think this came from just a suburb in Chicago, these house prices are way out of date. So just by looking at this, the bottom quartile, the top quartile, I can say, is this a good data set or not? So obviously it's not a good data set for predicting house prices in today's market, but you can always go and look for a more recent house price data sets. And for the purposes of learning this, it's perfectly fine. And something we looked at again on Tuesday, very, very useful, using the Seaborn library. We're using a histogram plot, and that has the default bins and all that kind of stuff. And we're going to look at the distribution here. So another very important point about this distribution is, data profiling is not just about looking at raw numbers. A lot of times when we're trying to evaluate and explain data, what we're doing is actually looking at visualization is a pretty fantastic tool for understanding and profiling of data, because this also is where I would say domain expertise comes into play, because you can see right here that this chart here is right skewed, right? And knowing what you know about real estate, you would say, well, that makes a lot of sense, because you're not going to give unless you're they're giving away those rural houses in Italy. Where I don't think they're quite giving you money to take the house off their hand, but you can get them for €1, and I think they upped the price to 10,000 or 50,000 now. But that was in the news. But generally, there's only so much you can go to the left. So you could almost say this looks like a standard normal distribution, except for all this stuff here. So it's right skewed, and with a lot of things, you'll see that right skewness. Right, it's pretty common. Other domain data sets. Let's say you're in finance and you're doing financial planning. I think this is a use case I came across in my career where the data didn't look right to me. Was it left skewed? And I didn't expect it to be left skewed because, some people can retire when they're 45, 55, but generally people tend to retire at 55 and above, right? So the 55 and above is around here. And most people tend to retire around 67 or 68. I forget what it is, whatever Medicare kicks in. But people generally don't retire after the age of 99. I'm sure you can guess why, right? So you would expect that distribution to be left skewed, maybe standard normal, a little left skewed. So just by able to look at your data, I can see straight away that this is a good data set, a good representative data set. So again, understanding your if it's left or right, and that's what we call the distribution. Now, so straight away, I see a problem. And again, I don't think in terms of math. How did I learn this? I guess I learned it the hard way, but you can tell straight away. We have tabular data. I'm probably going to try a linear regression model against it, or some kind of regression model. And linear kind of means linear. And linear models, they like to have a normal or standard distribution, and left or right skewed distributions are not normal, they're not standard. So that, and again, this is on sales price, which is the actual target feature. So for the most part, I'm going to leave that alone. I could do a log in it, but if I was plotting, say, the square footage or something like that, I'd say, okay, well, I want to use a regression model because I think that'll be the best one. So I may have to manipulate my data to kind of like better predict in a linear fashion, right? So that's why visualizing some of these features is kind of important to see what you would get out of it. And again, of course, we look at techniques to doing this at scale. Correlation, we covered that on so what did I skip here? Yeah, we covered correlation, the heat map. So you remember from Tuesday this heat map, and you remember how to read a correlation map. So the diagonal is they're all correlated with itself, and I think here's sales price, and this one doesn't give you a number actually. It's just doing from hot to cold. What am I doing here? I think I'm doing dark red is positive correlation, and oh yeah, dark red, of course, positive correlation, because everything's absolutely correlated with itself. So you can run that yourself, and if you're not familiar with it, again, just read this text here, And now, in our first step before we do our modeling, we want to figure out which features are correlated, both positively and negatively correlated. So people sometimes make the mistake, oh, this is negatively correlated, so I want to get rid of these. No, the ones that actually don't make a difference are the ones that are close to zero, right? The month sold, as predicted. Who cares what month? Actually, it does matter. Here in New England, I've seen you generally getting a better price. Sorry, you generally get a worse price if you sell in January or February. If you sell in April, you'll get a better price because April, May is when people want to buy houses so they can move their kids into school districts or whatever. So it's not absolutely zero, and I think in certain areas it can have something. This is in Chicago, Illinois, so it should have been pool area. I don't know. Sometimes pools are positive, sometimes negative. Interesting here that ID. This is a good example, right? ID should have no correlation because it's just a numerical incremental number assigned. It should have no correlation one way or the other. So it just makes you think that maybe I should ignore everything. It's kind of like this. So the ones we pay attention to are positive correlation. And all that means is as our target feature, the sales price, this is our target feature. As the sales price goes up, as one of these goes up, the sales price goes up, right? If I'm trying to sell tickets to a concert and I don't know, the closer it is to the city center, maybe the higher prices I can charge because there's a built-in audience. Negative correlation is the opposite, but it's still good, right? Maybe it doesn't mean good in this case, but let's say if I want to predict the it's been so cold here in the Boston area. If I want to go skiing, a good predictor of skiing is how cold it is, because I was too busy last weekend, but it was 40 degrees out, and I'm like, the sun was shining, but it was 4 degrees, and of course, perfect day to go skiing, right? Sunny day, but still cold enough not to have slush under your feet. So as temperatures drop, you'll probably sell more ski tickets, believe it or not, right? Because it's like, if today, do I either play golf or do I go skiing on Saturday, right? And if it's nice and warm, I'll play golf. If it's still cold and the resorts are still open like they are here, I could ski. So don't throw away negatively correlated. There's lots of cases for that as well. So, but in this case, they happen to be negative correlation here. So you can see some here. So again, take a look at it and take your own interpretation of it. And then here's scatter plot with a regression line. So again, in Seaborn, very simple to do. We have this regression plot method here, and we add our KWS line. We went over that. And we talked about scaling, standard scaling, and normalization. So I'm not going to cover that again. So take a look at this code yourself. Standard scaling and normalizations. And I think I picked two here. So this was our distribution of living area before scaling. And if you look at the charts here, you're like, they look the exact same, right? Exact same, right skewed, the hump here, here, and here. Nothing's changed. Well, it has actually changed. Look down here. So it's scaled from -2 to 8, right? So doesn't really look like much of a standard distribution to me, because it has the exact same distribution, which is fine. But this one here is scaled between 0 and 1 for this one here, because in living area you don't have a negative values. So this one here we scale between 0 and 1. So this one's min-max scaled normalized, and this one's standardized, right? So it'd be good for you, after all I told you, to take a look at this code. Pretty straightforward code. We are using a standard scaler method here from scikit-learn. See scikit-learn, we're using a standard scaler and a min-max scaler. And we're getting the scale values of those. So we're passing in that living area from the house data frame, and we're standard scaling it. I wonder if I made a mistake there. I wonder if I normalized it after I scaled it. because usually, because see the way I'm passing in the house data frame and then I'm scaling it within house data frame, and then I'm applying min-max scaling to it again. So I may have made a mistake there because you know, when you transform a feature within that data frame, you don't want to apply a different. Or actually, wait, did I? Yeah, it is both. It's I did it on group living area, so maybe that was a mistake, but it kind of looks right. Maybe, I don't know. And then you can see here the scaled mean is still off. Well, that's the scaled mean. That's not the standard mean here, but I should print out the others as well so you can see how that's changed. But the most important thing to remember here is, even though we've either normalized or standardized it, the distribution is still the same. Okay, so that's notebook 1. Yeah, missing values. You know, yeah, context is everything. That's, you know, when I always say, you know, never trust the AI models. This is one of the reasons I don't trust them, because at the end of the day, it can be a very important decision. Do I put the mean in? But what if the mean has a very wide, like if someone, if the average is say 10,000 and the distribution, the min max is between 5 and 5 million, what does the mean of 5,000 mean, right? If it's a categorical variable, and they have a very like a non-normal distribution, like maybe almost like a uniform distribution or something like that, or whatever. What does the mode really mean, right? So there is no hard and fast. Well, people will tell you there's rules of thumb. Sure, there is, like everything else. But I would look very carefully at the data and make sure people understand why you're and how you're filling in those missing values. Because if it's something that and how would you do that? Like you could try and fill in missing values different ways, and then run the model, and then test the model and see which comes up with more accuracy. And you know, is it causing my model to skew one way or the other? Like a lot of machine learning and data science, it's not like coding where I'm going to understand what my objective is, and then I'm going to write down, do my analysis, and figure out what features do I want in this software, and then write out the software, and then test it and it's done. No. Data science, and you see this even with generative AI as well, it's very cut and dry. You keep trying it, and then you start to use tools that can kind of speed this up. But it's not uncommon. Like, look, when we do hackathons, do you like, actually, this is a good when we did an NVIDIA hackathon at Audi SC West, it was pretty awesome with some pretty cool prizes. I think it was 50 grand prize of various stripes. And we had something like 1,000 people apply and 300 teams, and we had two different competitions there. One was around predicting Halloween costumes people would use for Halloween. The other one was around what did we do? It was some tabular data, but the kids, I shouldn't say kids, because actually there was a few student groups there, but it wasn't uncommon to them to run these models 400 or 500 times over that. The hackathon was over 2 days, literally 400 or 500 iterations of that, doing nothing more than trying to get squeak everything out of your XGBoost. And then the algorithms, you know, there's some hyperparameter tuning there, but it was mostly working with the features. And one of the tricks they did on the Halloween set, they were kind of like, you know, face masks are kind of all the same, because there was different types of face masks in the data set. And they were like, you know, I'm going to combine those 4 features into one. That had a big lift in the model. Like, why? I don't quite know. We always ask people to explain why your model worked. They're like, yeah, I did some feature engineering and I combined some features. But you ask them, why do you think that worked? I'm like, yeah, I don't really know. So that's fine. Don't have to explain. Don't have to always understand how the model works. The last code segment was should just shown. Absolutely. So again, so this, what we're trying to do in this code segment here is scaling and normalization. So I just did a whole spiel on scaling and normalization. I think you got that part. If you don't, go through the previous slides and read this here, right? This will tell you it. So what we're doing here is we're using scikit-learn, which is our library, and we're using two of their scaling methods, the standard scaler and the min-max scaler. And there are two different kinds of scaling methods, right? So again, kind of explained one of those. That's the standard standardization, and this is normalization. I know that sounds very, I don't know, normalization and standardization. It's the way data science is kind of named these super confusing to people. I know, but and remember, you can always go to scikit-learn and read what it says actually in the method here. You can see I got a little verb here. You can open this in the new tab, same one here. You can go look at this one as well here. And again, normalization, fixing it to a given range, right? And that's the pretty common one here we use. And now we're just doing, we're plotting it. We have a number of bins. So we're just saying 30 bins here. And what we're doing here is we're taking the living room area, we're transforming it, and we're doing fit transform. You can see that method here. It's fitting this to a standard scaler. So that's a function with our standard scaler module library. And then we're assigning that to, oh, actually I didn't do this wrong. So I was smart enough to give it two new columns, group standard scale. So that's a new column within house data frame. And here I'm doing similar, but here I'm using normalization. I'm using min-max to min-max when I'm creating a new function. So I actually got three columns around group living area now. I got group living area and the standard scaled and the min-max scaled. And then all I'm doing here is just plotting it out, right? Plotting it out. And then here I think as an exercise, you can do it on the min-max here. And that gives me the three graphs. So this is the original one here. Group living area was between, I don't know, 500 square feet and 5,000. Now, this is the standard scalars between -2 and 8, because we still have these outliers. And this one's min-max scaled. So hopefully, does that make sense, Neeraj? All right, so if that's good, then let's go to lesson 2. In lesson 2, let me clear my code. Yeah, so lesson 2, we're going to finally get into feature engineering, model selection, and model training, right? So pretty important. I'm going to skip through this pretty quickly. Loading in my data again. Another reason to run this kind of like locally, because you don't have to keep doing that. I'm going to clean my data set. And again, just looking for nulls. We looked at that. And again, doing something pretty simple here. What are we going to do here? We're going to fill in these ones here. We're going to update our in place equals true means update the data frame we've been working with. And if it's categorical and non-numerical, we're going to get the mode, i.e. the most frequent value. And if it's numerical, we're just doing the mean. Again, not advocating this to use this every time. This is very crude, but maybe it doesn't make a difference. I would have to try other kind of, there's more advanced techniques like Windsorization. Lots of different techniques you can try to fill in missing values, but for the sake of doing this, but look how quick this is. What we're doing here is for each column, we first look for in a for loop for each column as an object. For each column, we iterate through all the columns, which are features. And we're basically saying if it's an object, get the mode, and if it's not an object, else get the mean and update those missing values. And then I quickly check. And the great thing about a data frame is you can take one function, apply to, remember a data frame is a kind of a grid, a matrix. I can apply for every single cell and variable in that matrix. Is there any nulls? And it's saying no nulls, right? So we've got rid of our missing values, albeit in a very, very crude way. Now we want to do some feature engineering. And the classical way of doing feature engineering is, and I think actually that was one of the winning ways, is just concatenating columns, right? So, you have in a house, you've got, I don't know, a suburban house, you've got maybe attic space, basement space, first floor, second floor, living area. We'll just add it all up and just say total square feet, right? because usually the less features, the better, as long as you're not dropping features that have predictive power. Less features is better than more features, generally speaking. And so combining features, like maybe people love a huge basement, and maybe it's a bad idea to add these in. So again, try it with it and try it without it, right? So again, kind of get out of the mindset of like, because you may be there and you may have 50 questions. Well, how do you know to try this and how do you know to try that? Just like the folks in the hackathon, you over time you may kind of develop that sense. You know, you just kind of get a sense for it. There may be tools that can help you with that, but for the most part, it's cut and try. It's trial and error, right? Well, trial and measure, not so much error, hopefully. So that's an example of we're combining features. And then very important, we want to encode on hot. So categorical variables, we want to encode those. So we talked about one hot encoding, super quick refresher. You take a categorical variable, or you can even do it as non-numerical. So these are non-ordinal, by the way. There's no order. You might have a favorite color, but it doesn't matter, especially the machine. So red, green, yellow, and because there's 3 values here, even though I've got 5 listed, there's only 3. So I would create a 3-dimensional vector array, whatever you want to call it, and I would encode these with ones. This is what's called sparse encoding, because it's called sparse because imagine you had 1,000 colors, and for the most part, it would be just filled in with zeros. So red is 1, 0, 0, and then here's red repeated, 1, 0, 0. So that's one hot encoding. And again, when we did our machine learning data prep, we went over all of this, and we actually, if you look at those notebooks, there's more examples on one hot encoding. But for this here, how do you do that one hot encoding? You use what they call dummies, which always throws me off, because when I think dummies, I think dummy variables, which means something else entirely. So for each categorical feature, non-numerical value, because remember we looked at those, like for what was it, zoning types, was 5 different zoning types. How are we going to represent that numerically so we can put that in the model? So we're going to create of those 5 unique values, we're going to create 5 new features, one for residential, one for that, and that's good because I forget what the other features were, but one is residential. I would expect that to have some impact on the price, because you know, or maybe it doesn't have an impact on the price, but maybe if one is mixed use, because who wants to buy a house next to an industrial park, right, or in the middle of it? So maybe there was the zoning that says mixed use, and that should have a negative correlation to price, right? So that's why breaking those features out, if you think about it, now you give the model a chance to, like, instead of just having one feature and trying to figure out the impact on the target feature to sales price, now I can look at each of those categorical values. And I'll tell you one very famous example, which you probably may already know or guess, in real estate, and that is neighborhood, right? And again, the beautiful thing about machine learning and pattern matching is, and you wonder how our brain works, the machine knows nothing about neighborhood, just like you. Like, where are these neighborhoods from? No clue. Some place in suburban Illinois, outside Chicago. No idea what Breedale means. Maybe it's Bridgedale or something, or Northridge. But for some reason, when you make this Northridge and say there's like 500 houses in Northridge, for Northridge and sales price, whenever the house happens to be in Northridge, when Northridge is a 1 and everything else is a 0, the prices tend to be high relative to everything else. Whereas in names, it tend to be lower, right? So very classic example, which you know yourself. You ever look for an apartment, says, okay, I like this neighborhood, I don't like this neighborhood. This one's too far away for transportation. This one is too noisy, you know, whatever. This one's too sketch, as you kids say. So that's a classic example in real estate. You almost want to model by real estate, by neighborhood, right? So these are all the features we want to create features from. And then remember when we did that, so how do we do that? So here we're just printing them out. Not going to go over that again. So we're doing, we're using get dummies. And this converts categorical variables into dummy indicator variables, which is 0 and 1, which zeros and ones is, where's my one hot encoding? Zeros and ones is what one hot encoding is, right? That is what one hot encoding is by definition. So what you're doing here is you're getting the categorical variables and getting your encoded. So now I've got a subdata frame, and see here I have the same number of rows, 1,460, but now instead of having 81 columns, I have 290. I assume all you guys can see my code, right? If you can't, I can zoom in a little more, but let me know if you can't see it. So now I've got, because remember, so again, I'll go over that real slowly. So let's say there's 10 neighborhoods. Instead of having one neighborhood feature, now I have 10 neighborhood features. Instead of having one land sloping, I have one feature, I have 3. Here we got 2, here we got 5. So that's how I jump from 81 to 290. So pretty big deal, right? And when we say print shape, it's like a print matrix here. So see the building type: 1 family, 2 family, duplex, townhouse. These 2 townhouses are the same thing, I would imagine. That'd be a good way of like, this is definitely a feature you want to combine, right? Because maybe one's a typo and one's not. But see now, these are my 5 new features based on those values, and they're all one hot encoded. So now let's look at feature transformation. Okay, so there's again, log transforms. You know, if you remember your log, it kind of like, you know, reduces out the really high numbers and kind of cleans up your numerical data. But log transforms are pretty useful. You want to use them, especially if you're doing regression or something like that. Then it's always a good idea to get the log. So what am I saying here? Yeah, because we've got these varying variables. So log transform here can be quite useful. And we have a right skewed distribution, right? So log transforms are generally good for right skewed distribution. So how are we taking care of this? So I'm just checking if I have any questions, because usually I have a few more. Okay. So here we're using a NumPy library for log form, and we're using 2 of our matplotlibs here. So here we're just simply getting the log. Right. We're coding the total square foot into log total square feet, and then we're plotting out the original and the one that was transformed. So you see the effect here. So total square feet, which I believe we just calculated, we combined that. You can see it was right skewed here. And by simply applying this one little log transform here, now we have something that's standard, normal, Gaussian, normal, whatever your preferred technique is in that. And that should work better for modeling with regression or any kind of regression technique, or KNN, or support vector machines. And see how it's able to do that, because, you know, it did a log transform. So you no longer have the scale down here, but you do have this. But for the most part, it's preserving that distribution, because again, you know, most of our entries were around here, around the central tendency in the middle here. And for the most part, you still have that, right? So pretty cool. Never much like math until I started doing data science and AI machine learning. And now I'm like, okay, now I find a use for this. Removing unnecessary features. Remember we looked at the ID column, right? It shouldn't have any transformation. That shouldn't have any impact in that. Maybe we remove pool, maybe we remove fence and stuff like that. So we're removing that. Don't know why that's not working. Why is that not working? because ID is not in there. Oh, I think I dropped it earlier. No matter. Now feature selection. So we've cleaned up some feature. We filled in the missing values. Now let's go into some feature selection. So usually when you want to do feature selection, generally speaking, sometimes you can be working with a data set with less features, but more often than not, you'll be working with a data set with many, many more features. So you want to kind of use some kind of threshold to kind of bring them down, right? So because we're looking for positive correlations for the most part, and maybe some negative ones as well, depending on what they are, we're going to do a threshold between 0.5 and minus 0.5. Should it be 0.6, 0.7? I don't know. Again, when you do kind of cross validation, you can hyperparameter choose this, and you have there are functions that will go through that range of values for you and kind of run them in the background. It might take 10 minutes, depending on your machine. It might take a half an hour, but it'll figure out for you what's the optimal threshold, right? So right now, I'm just picking one. It's not very scientific. You know, 81 features probably might be all right. So I'm just picking a threshold. Let's see if this works. And I'm dropping sales price because that's the target feature, and I don't want to skew that. So what we're doing here is just setting a threshold to 0.5, and it's correlated with itself anyway. And we're looking at sales price correlation. Remember that. And if it has if the target feature, sorry, if the feature has a strong correlation over 0.5 with the sales price, we keep it. If we don't, we drop it. And you can play around with this. You can set this to 0.7, higher, lower, and see how it goes, right? And here are the features it's selected. So we've done feature selection, and we did it in a very, very simple way. We just kind of crude. We're saying like that. So what does that look like? It looks like this. So not a whole lot of features, but we believe these are the strongest positive and negative correlation. Because you want both, right? You want the ones that are strongly correlated, strongly positively correlated and strongly negative correlated, right? And again, this one is goes from red to blue, which you can see. So you can see here for sales price, the most strongly correlated feature is overall quality. And now year built is next. Actually, no, these are not ordered. Sorry. Total basement is year built is not that strong. So the reds here, total square feet. That's another close winner. And log total. Then we did our log. We did our total. We took our total square feet and we did the log one. Total square feet. Where's total square feet here? Yeah. Didn't really change it much. Went from 0.78 to 0.76, but again, demonstrated purposes. All right. So, and remember, yeah, correlators. Okay. So, what am I doing here? So, yeah, external quality TA and sales price. So external quality TA. Let's see, where's external quality TA? See, this is our most negative one here. So it's always good to look at those negative correlated and try and understand the relationship between them. And here what I'm doing is creating a box plot, which we looked at on Tuesday. So we want to take sales price and describe that as well as external quality, and then map those. So good to look at the mean, the standard deviation in those. And you can see here sales price versus that. We still have the outliers here. Yeah, so overall quality 0.79, ground group living area, garage area, and darker areas. Okay, so not sure if this is useful for you, but kind of good to kind of get an idea what is going on here. All right, so is that the last of it? Oh, sorry, this is another technique, RFE, recursive feature elimination. Um, it's a more advanced way to figure out the best features, a little more sophisticated than just using a selection one. You still have to set a parameter of how many features do you want? Do I want 40 or 60? So again, this is something that you might want to feel into the algorithm, try 20, 21, 30, 40. But this is um, would I say it's better? Yeah, probably RFE. And but for the most part, see, it's kind of selected the same features: quality, sales condition. Interesting, it picked pool quality, which I wouldn't have expected. So maybe it's worse actually. Um, and okay, so you probably have some more questions about that, but let's move on to actually running a model, because this is the meat of it, right? So we have all this data, and I have to go a little slower here because there's only a few lines of code to run your model. So first of all, we're going to use the scikit-learn library, which again, as I mentioned, is excellent for this. And as mentioned before quite a few times, what we want to do is first get our data set and split it between training set and test set. And so you may have all been wondering, how do I do that? Well, you just use this train, test, split method from scikit-learn. You can set the test size to 0.2. That's out of 1, so that's 20% versus 80%. Random seed, this can be important because you set your random state to any number, doesn't matter what number you set it to, I believe, at least when I was using it. Set it to any number. And what that means is when you rerun the model again, it should, if everything else remains the same, you should get the same outputs. Right? If you don't set this, you get a different result every time. And why is that important? Because if you're trying to hold some sub steady and measure other outcomes, this is kind of important. So it doesn't mean that it'll never change, because let's say if I change the test size to 3, of course the output will change, but all else being equal, if everything else stays the same, using the same random states, you should more or less get the same model. So it makes the model reproducible, right? Reproducible, as I'll say here. Yeah, I say whatever. I say random state 17. It can be any number. And we're going to use a linear regression model here. Very simple linear regression, which we covered on Introduction to AI, if you're not familiar with that. So, and then once we get that, this is the model that actually trains our model. So fit means basically the trainer, right? So that's, you're basically, as the text says here, you're instructing the model to learn the patterns, or learn the relationship between our target feature and our sales price target variable. So yTrain contains our target feature and our dependent variable, and this here contains our independent variables, our features. And remember, we only selected, I don't know how many features we selected, maybe it was 20 or so. So again, we kind of explained this in detail here. So let's try it. Let's run our model. So here we're using various models here. Yep. And what we're doing here is we have our selected features. So we have 20 features we selected, and that's our X selected, and Y is our sales price. You see that splitting up. Now we do our test and training, and we're picking the model, which is linear regression. So on linear regression, we're saying model, fit, X train, and Y train. So we haven't printed it out yet, nothing yet. All we've done is we've trained that model. And because the linear model has been very quick, right? So we've just trained the model. We haven't done anything with it yet. So now what we want to do is make a prediction. And that's a pretty simple method. It's just model.predict, right? So remember, we have our test set and our training set. So with our model, we're going to see how good it is at prediction. How are we going to know how good it is? We're going to take the test set that we held back, and again, look for that loss margin between the predicted value and the actual value. So if we had a test value, just to remember that if our model predicts the value of 480,000, and the actual price was 500,000, then we're off by 20,000. That's the error between the test actual value and the predicted value, right? So let's try that. So here we're doing our train test split again, linear regression model. Now we're going to use an evaluation metric, and we're going to use a very common one for linear models, which is mean squared error. Very similar to what the name suggests. And now we're also going to use R-score. So here we are using that model.predict with our test set. So you can see our test set here. See our test set had 292 values, whereas our training set had 1,160. And by the way, maybe I went through this really quickly, but see the way, especially from other languages, it's very unusual to call a method or a function and have it return 3 different variables. But see, this one here returns the training set, which is out of the 1,460 rows. The training set was 1,468 with 20 features selected. Test set should have the same number of features. That's very important, but it's only got 292 rows. And then we have our Y train here, which is the target feature, right? So that's where those values came from. And again, we have our predicted values here. So we have an array of 292 predicted values. And now what we can do with that is take our predicted values and get the mean squared error. Just calculate the error, the mean square of the error between our test values and our predicted values, right? So here, because you can mouse over that, you can see there's all kinds of, that's an array as well. And that is 292, right? And oh, here we're doing a prediction again, right? So now we're doing our Y predict. Not sure why am I repeating that again. That line shouldn't be there. That's just a repeat. Oh, am I doing it because I think I'm doing it because I want to get the mean squared error, or maybe not. No, anyway, that line of code is redundant, but ignore it. Now I'm getting the root mean squared error, and there we have a value of 42,060, and then we want to get the R scored as well. All right, so you've got all kinds of questions you're asking. What the hell is root mean squared error, and what does it look like? Well, this is what it looks like, folks. Lots of decimal precision. So this is our these are our predicted values from our model, and you can see 1,408. And that's kind of like very similar to the mean. We you know, that's standard normal curve. So that's our predicted values, and it has a root mean squared error of 49,069. So this is why I don't want to, and this is the reason why I keep the random variable set to a certain number, because now I can explain to you. You go back here. So that's the square root of the mean squared error, and provides, you know, so this 49,619 mean on that. On average, our model predictions are plus or minus $50,000 away. So would this be enough to go to Zillow and say, hey, I got a new model that's better than your old one and you can predict house prices now? Probably not. But if someone's kind of typing in, how much is my house worth? 50,000 off a, what's the average house price? 350, 400. It's pretty, what is that? Maybe 84% or something. Not even. So not a great prediction. Maybe good for a toy example, but that's pretty far off, right? This root mean squared error, or sorry, R squared error in conjunction with that is also very insightful. So what we're saying here is there's a 64% of the variance is explained by our model's predictors, right? So I would say 64 is not great. It's not as bad as you would think it is, but it's not great, right? It's better than nothing. But remember, this is out of the box, no tweaking, no hyperparameter. This is our first case. And what a lot of data science and machine learning engineers will tell you, just try the most simple, simplest model possible. Get a prediction, and don't worry about it. don't get freaked out if it's below 6, if it's below 80 or below 90. That's what we call our base rate, right? That's our baseline model. And now from there, we try and improve the model using our skills, right? And again, like you could give this, and this is where kind of like in Notebook, you give it that sample data set, tell it to do a prediction, and maybe it won't get another good one. You have to work with that AI code to improve this. So we're going to work with that, right? So so that's what we're getting. So it's okay. It's a baseline model. It's not the greatest, but that's fine because we did something very basic. So a better way to look at this is let's plot this out as well. So here what I'm doing is the test versus the predicted. Instead of just getting the root mean squared error, the R squared, I'm plotting them out. And do you notice something here? This is the prediction line because it's a linear regression model. This is the predicted line. Around here, does a pretty good job. Wheels come off the bus here. Wheels come off the bus here. And you know why that is? Because remember we talked about linear models. They don't like, they like standard normal. And now you see it. Because these numbers here represent that right skewedness, right? Right skewed. So when I have data, I'm like, okay. And again, with experience, you'll start looking at the data set. You know what? Maybe I'll try a linear regression model for my base rate, but I know it's going to be not my final model because my data is right skewed, and I don't want to normalize or standard normalize my target feature because that's the thing I'm trying to predict, right? So right here, you can see the wheels are coming off the bus. All right, so and you'll hear this. You'll hear people talk about actual versus predicted a lot, and one thing you need to really pay attention to is what we call the cost function. I think I kind of call it the loss a lot, the loss function. So again, it's basically a measure between the predicted output and the actual target values. I talked about that a lot, right? And there's different ways of measuring that cost function or that loss function. So root mean squared error and then root mean squared error is kind of that. And there's kind of lots of metrics there. I don't kind of freak out too much about which one should I use and which is a better one, because what I'm kind of like is looking at this stuff here. I just know it's not here. Like sometimes a scatter plot will do fine, right? And sometimes looking at a scatter plot actually gives me more information, because here I'm looking at a single value. Up here I'm looking at a single value. Here, by looking at this, and this is why, data visualization is such an important debugging technique. It's such an important explainability technique. Because yeah, like, okay, you got a high, and trust me, if I got rid of all these outliers here, I went back to my boss and said, look, we can't predict house prices over 600 or 700,000. Let's go gather more sample data. Don't forget, that's a way of improving the model as well. Get better data. Maybe produce some synthetic data and really fake it out. So again, visualization is your friend, and that's why it's always a hot topic in data science. That's the cost function. And then cross-validation. You remember we talked about cross-validation somewhere here. Somewhere here. Too many slides. Anyway, we covered cross-validation, and we just covered it a few minutes ago. So I assume you guys remember from a few minutes ago. But cross-validation, as I said, instead of just doing one test and training set, we shuffle it, and we're doing five different splits between test, and we're moving the split 5 different times, right? And let's see if that gets it any better. Because why do we do that? So yeah, across 5 folds. On average, the squared error predicted house price very large given the house price range. Yeah, 34,000 versus 40 whatever. What was it before? 40 something, 49,000. That's better, right? So with that one little line of code, we've actually improved it. Sorry, where am I? I'm lost. Yeah, with that course validation of 5 folds. So again, excuse me, hyperparameter tuning. What if we tried 10 folds or 9 folds? There is a bit of diminishing returns, and there are algorithms out there in scikit-learn which will help you run this multiple times. So again, it's almost like a nested. So cross-validation is kind of a nested function in itself. but now I'm going to nest that in something else, which is going to run this exact same thing across these. And notice I'm only actually looking at group living area this time. I'm not doing it across all 20 features, which is kind of cheating a little bit. And then I'm saying splits 5. So that's something that's cross validation. Very, very simple technique. Generally speaking, you know what the right value is, I don't know, but generally speaking, you always want to do cross validation. It's a pretty newbie error to just do a single split, because who knows if 70-30 is better than 20-80? I don't know. And then who knows if 4 folds is better than 7 folds? I don't know. Again, every test set is different, and why we do so many iterations. Here we're going over the root mean squared error. That's a bit of an explainer on that. So very important. We covered this in our AI literacy, but a lot of features are not, because we can see, for example, as the houses, now it's a bit of a skewed data set, but we notice in our data set as the houses get bigger, the prices are no longer linear. And I can illustrate that by just looking at this here, right? So imagine this was the square footage of the house here. I know it's not, and this was price. You would see these two outliers here, right? So instead of being a straight line, it's kind of curving this way, right? So now, if you remember back to your math, what we want to do is we want to predict the slope of the curve, right? And to do that, we're going to use a polynomial regression, which I go into here. And again, Christ, do I remember this formula, this math? No, I have a vague idea of it. If you asked me to build it out, I wouldn't know how to do that. But I do know, I think, if I think my data doesn't look linear, I think a polynomial will probably work better. I can use polynomial features from this library here. And again, you know, even this one here is not, it's not linear, right? So we're going to try a polynomial. So here what we're going to do is I'm just taking 2 features, the target feature and a strong independent variable feature. I'm going to use my linear regression again. I'm going to do some cross validation. I'm going to score that. So that's fold here. Oh, sorry. Yeah, that's like, where's the polynomial here? Here I go. This is the polynomial feature. Let's see here. What are we doing? Yeah. So, you know, your polynomials, second order, third, quadratic, different types of polynomials. So we can try a third degree one here, and then we're going to try and do a fit transform to that variable and plot it out. And here it's giving a scatter plot like this. This is actually the first set here. We plotted that out, just the original state, and then we're doing our polynomial regression line. So what I'm doing here is, see, I'm trying to get that line to fit, and you know, it's hard to know. Like, you've got outliers here, you got outliers here. You can actually, which is the best line here? Is it this one? Maybe that's a bit overfitting. This is overfitting to outliers. And the whole idea about outliers is maybe you won't see those outliers again. So that can be a problem. So maybe one of these polynomials are a better fit. So what I'm doing here is, we're creating a number of different lines here, as you can see. So plotting it, and then prep, movement squared error, figure 86. And yeah, so play around with that and try different features. You can try, you know, total living area. You can try number of cars in the garage, and that should be quite useful. And interesting the way it kind of slopes those lines there. Okay, so that's the second notebook. All right, let's go to the third notebook, which I think I had a problem with this one, but I should be good. So there's no questions in the second notebook. This is the last notebook, you'll be glad to hear. So what is wrong with my cat boost? Come on, cat boost, don't fail me. But no matter, I just had an error when I was, which I'll go through here, so it doesn't really matter, but we'll figure it out. So, what do we want to do here? So we saw our results from last time. They weren't that great, right? That's not a, you're not going to win any Kaggle competitions or any hackathons with that, right? So what we want to do here is we want to get a better model prediction, right? Because that's why we're in the room. We want to do more accurate predictions. So again, same data sets. And because I'm getting the data set raw, we're doing our whole dummies one hot encoding. So I'm just doing that in one line of code because again, we're on a new notebook here, so we have to kind of restart from scratch a little bit. So what I want to do is try different types of linear regression models. So a lot of times when we're doing with linear regression, as I showed you in that last notebook, we're dealing with overfitting and underfitting, right? So, you know, this one here I think is overfitted to the model. This one here might be underfitted. So overfitting means it's predicting too well. It's almost like and actually no, our linear model certainly did not overfit. In fact, if anything, it underfitted. And I should talk about that, I guess, first. So underfitting is when the model is too simple to capture the underlying patterns of the data, right? So here, if this is a linear model, it's not capturing these patterns of the data, right? This one here is almost like overfitting to here and underfitting to here, right? So people talk about underfitting, overfitting all the time. So underfitting means the model doesn't do a good job capturing the pattern of the data. How do you know? Because when you do your evaluation, the cost function or the loss function is too high. The difference between the actual and the predicted value is too high, right? And overfitting is kind of weird. You're running your test and it's like, wow, I've got 97% accuracy. That's pretty good. So a bit of a Jekyll and Hyde personality when it comes to data science. You should be very suspicious of that because generally speaking, when you go out into production, all of a sudden your model's not working that well. And you're like, why is my model working that well? Because it's overfitted to the training and test data, right? Because maybe the training data represented the test data very well, or vice versa. So, and another kind of thing here when we think about regression lines is remember the coefficient. The coefficient is, say this is a regression line, it's not, but this it's the measure between the difference between these two values, right? So it's just a value. Yeah, it's not quite as simple as that. It's just a multiplication of the term, if you remember back in your coefficients, because that's kind of key. Because what I want to talk about is ridge regression and lasso regression, and they work on better fitting the model to this, and they use there's another term I see in here, regularization, right? So whenever you see the term regularization, L2 regularization, usually what we're talking about here is you're trying to prevent overfitting, and I think the technical definition of it is you're adding a loss function. You're adding a penalty to the loss function, and what you're trying to do there is, because it's overfitting, you're trying to discourage overly complex model fitting or model stuff like that. So what you do is you're shrinking their coefficients, that value there, or you can also solve this by getting rid of irrelevant features. So that's, and we use lasso regression is a good job on that. And that's also when we're talking about, like, when people say things like, well, you want to get rid of your irrelevant features. Like sometimes I remember, well, why am I doing that? Well, because it can lead to overfitting, because the model is trying to fit on features that have no bearing on the output of the model result, right? So So something to remember. So always kind of try and remember, like, why is it doing what it's doing? So let's see here. Do I run this here? Yeah, run that. These are our two of our models here. And there's lots of different parameters we want to look at here. Let me see what time it is. 3:50. We should have time to go through these. So there's a couple of things here. We want to look at the alpha parameter. Is the strength of that regularization, right? Actually, yeah. So I wrote down here what I meant by that. Prevents overfitting. So I guess my memory's not too bad. And then we want to standardize some features. We talked about that before. So let's try this out and see how it looks. So we're using our standard scaler, which we used in the previous notebook. We're fitting the model. We're transforming it. We're setting our ridge to 1. Again, this is a hyperparameter. You can tune, you can try different values. And we're using that ridge, we're fitting it, and then we're predicting. And now we're seeing, well, did we get a better score? Right. So, and then we're doing the exact same thing for Lasso, but Lasso is a bit different. It tries to converge on the best value, but the best results by doing a number of iterations. So again, here we're doing 20,000 iterations. You could do 5,000, you could do 30,000, 40,000, but you'll see one will underperform, other ones will you'll get worse performance with running a lot slower. So again, I'll let you kind of like read those functions and get a better idea of what they do. So best thing to do is just look at it, right? So if you remember back, this is a perfect fit. This to me straight away looks better. This is a better looking model than the one we had before. So remember what we're doing here is the predicted sales price versus the actual sales price. So now we're working on the target feature, and kind of hard, kind of indistinguishable between the two of them, but very similar thing here. And I think I explain. Do I have the model outputs here? Yeah. So now we went from 6.4 to 7.3. So that is quite a nice little bump. So we're out of the 60s. We're into 73. This one is still 68. So let's do, so the ridge regression seems to be working better. Remember, like the data set we have is not that big. But that's not too bad given what we have. So you can see that automatically, because as we expected, not all of our features were as linear as we expect them to be. And again, linear models expect a lot of our data to be in that standard normal curve, and a lot of our data had like various kind of skewness in relation to it. So we can see right away we had certain values here. Now, to improve this, like maybe with the Lasso, we try more iterations, we try a different alpha. That's what we call hyperparameter tuning. Which way to go? I would say, again, from my own experience, maybe Lasso increase the number of iterations. Not sure. We're using one alpha of maybe try 0.7 alpha. It may or may not help, but you'll see those numbers go up and down and kind of trial and error again. But see, we have a nice little result there, nice little bump, and yeah, iteration epoch, some here. So that's a lot of people use those terms interchangeably. What's this other question here? Yeah, that's actually correct, Kahid. Yeah. I think I get what you're saying here. Yeah, you're saying if you want to retain one of the models, right? Yeah, that is true. Maybe I'll add a little code to demo that in my next iteration of the notebook. And psychic pipelines are kind of interesting as well, which I don't really cover in this course because it's introductory level. So I talked a little bit about hyperparameter tuning here, the alpha and the ridge, and So we're getting them below, that should be 45,000, by the way, not 450,000. All right, so sorry. I talked about nonlinear models. Actually, they're obviously still linear models. So now we want to go into nonlinear models, and one of the most popular nonlinear models that have been very successful in industry and hackathons and competitions have been decision trees, right? So decision tree is quite famous, and the most famous decision tree is random forest. And by the way, if you're playing around with LLMs, like one of my favorite prompt engineering techniques now is called tree of thought. So it's kind of like almost a decision tree where it can take multiple paths. So knowing how these work is all comes in interesting. So random forest aggregator is an ensemble method. A lot of times these ensemble methods, they use what we call weak models. A weak model is something that doesn't give a very strong result, like that linear model didn't give a very strong result. So that's kind of a weak model. And if you combine, it's interesting, but over a lot of iterations of our ensemble technique, you can combine a bunch of weak models to get a better model result. And that's what boosting is, which we'll talk about a little later. All right, so random forest aggregator. So one of the things you want to do there is set the number of estimators, how many times you want to run that, and another one is the number of trees in the forest, so to speak. How many trees you want in the forest, and then I set my random states again, so it's reproducible. Number of trees you want to have. So common start at 100. I don't know why it's 100, but they say it's 100, and I don't know who they is. Maybe it's Andy Mueller and those guys. So you can see here, number of estimators 100. So I'm going to have 100 trees here, and I'm using my scikit learn here. Where did I pull that out? I don't like it when I don't put the libraries in here. So anyway, but this comes from scikit learn. And again, take a little time to read this method. Yeah, they call it a meta estimator, term I don't use. Controls overfitting, predictive accuracy, So we're going to run that. And wow. So we got an R2 score of 89. Now we're getting someplace. Now we're like, that is definitely a better model, because we're getting closer to the value of 1 where we want it to be. The mean squared error is still quite high, and again, this is not a house price or anything like that. It's just a number, and it's a number relative to, say, other numbers that we predicted the mean squared error when we looked at that. So we look at, you can still see this is quite high. So we're using house prices, and I explain here it's hundreds of thousands. So that's why that's kind of, because it's the root mean squared error, right? Or the mean squared error. So of course it's going to be quite a large number. But we are making progress here because this R scored is pretty good. Now we're saying 11% of the features are not included in the data set, are randomness in the data. So we're trying to get rid of that. So a couple of different ways. Yeah, so now we're just, you can see now we're getting down to 29,000, which was, what was it last time when linear was 49,000? Big difference, big difference. So now we're getting closer to, my house price is they're around 300, 350 range, $30,000 either way. That could still be good enough for a website to make some fun predictions. And even to go to a client, I can say, well, let's price it at 350,000, and we may be overpricing by 30 or underpricing by 30, which is in the housing markets, because you see like people bid way below or way over. It's not a bad predictor. Plotting the residuals, again, the difference between the predicted and the test is always kind of interesting. To predict those, pretty simple. We just take the, because again, we're working with data frames here. No, we're working with that is a series or an array, probably an array. So we're just taking the two, oh yeah, it's an array. Yeah, it's a NumPy array. So we're just taking the difference between the two, and we're just plotting the residuals. So again, the yellow line means there's no value. And yet again, I can see the higher the price, the residuals are huge, and it's really fucking up our model. Sorry, excuse my French, and apologies to the French. It's really messing up my model. Um, that's usually how I talk when I'm trying to do actual predictions in production. What the fuck is going on with our model? Why isn't it better? And I'm saying that to me. I'm not yelling at a data scientist. I am the data scientist. So nice little technique there. So again, now you can see now you can see why people really want to spend time in the data. So that's very kind of important. So what you want to do here is do that residual analysis and what you'll see as well. There's a couple about a couple of methods in scikit-learn. I'm trying to remember it. Let me see if I can Google it, which will allow you to print a whole matrix of these plots. Maybe one of you guys on here know it already. It allows you to plot both the coefficient plot between your features, or let's say you got 20 features, and which we've selected on the target feature, and then also all the residuals as well, because just plotting those out can be a lot. Let me see if I can find it. Yeah, I don't think. I forget what that is. I might have to include that in next. So most of your residuals cluster around 0. That's what you kind of want. So what am I saying here? Yeah. Yeah, 17,000 is pretty good. That's getting better, kind of in reflection to our R squared error getting closer to 1. And as mentioned, the house prices deteriorate over 380,000. There's ways we can do that. We can maybe do a log transform and sales price, which I don't want to do, but it's one here. Or we could try and find a better model, right? And we'll move on to that. So what else here? Oh yeah, so asking the questions in R2 scored. R2 score that is high and good versus one that's high and indicative of overfitting. Yeah. So generally speaking, what we're looking at here is, this fairly simple model we're doing is, an R2 squares it here. A value that's closer to 1 means the model is explaining the variability in the target feature, right? So it's fitting well. If it's less, if it's low or closer to 0, it's not doing much. Your model's explaining very little. And if it's not explaining very little, it's not going to do a very good job prediction. So that's one way of looking at it. But as you're suggesting, sorry, am I showing that question? Yeah, Jonathan, as your suggestion, that's not always the case, because a good model, again, that's why you want to look at the data in different ways, because that could be what we were just talking about. That could be overfitting, right? So that could be indicative it's not a good score. It might be overfitting it. So you want to be careful what you don't want to do that. You want to be careful with that. And again, R squared, you're only using that with regression tasks anyway. And that's why you also want to use it, apart from R squared, that's why we also look at root mean squared error and cross-validation and other techniques like that. So yes, a high R score is good, but as you're mentioning, it can indicate overfitting, right? But testing for overfitting, you can do that another way, right? So again, it's just a number. There's other ways of checking for overfitting. So, okay, so let's move on to feature importance. So feature importance, we've kind of already looked at that quite a bit, because there's like, how do you determine what's an important feature versus other ones? There's, this is, let's see here. So we're plotting these out. And here we have, we're using this random forest one, and it's telling us, which is a really cool method. It's not actually a method. This is a mutable value. It's telling us, based on what it thinks, what are the most important features. And this looks very, very different from that correlation matrix we saw, right? And kind of scary, because we see, if we didn't do a good job of collecting overall quality, that explains a pretty large part of it. So I would say I would not be happy with this data set if it was mine, because it seems that it's focusing too much on overall quality. And why do I think that's a bad thing? Because just think about it. I know the domain. I know the domain of real estate, and you could walk into a beautiful studio apartment with immaculate quality, and it could be priced at 500,000. And then you could walk into a 5-bedroom, 5-bathroom house. It's an absolute dump, but maybe it's in a much better location, and maybe it's a tear me down, and that could have a better price. So yeah, you can't model off one feature. So that's a very strong feature. And again, not going to kind of get into the nuances of that, but again, this is when you're building out your models, understanding why they gave you the results they did, the explainability. And people are always like, how do I explain a model? Well, there's so many ways to look at a model to explain it. So again, it's important to study the methods that you have at your fingertips. And so feature importance is kind of cool. And you can do this with different models, right? Can you have the model explain to you the feature? So this is kind of cool in random forest. So here's a way of improving and tuning your model. So this, notice in this course for this lesson today, we're not giving exercises. Well, there are some, but for the most part, what I want you to be doing is playing around with this hyperparameter tuning. So again, there are methods, which I can't remember in scikit-learn, that'll do this automatically for you, and it'll come out with the best version. But you're better off, because you're new, try it yourself. Try the depth of the tree, max depth, number of samples, splits, cross validations, max number of features. Try more features, less features. Because the great thing here about this data set is Kaggle. This was actually a competition. And this was the competition, right? So I'm going to show you some boosting techniques, but I should include this in my presentation, because you can do this yourself. So so I would say inspiration, and that's it there. So that's pretty cool, because that's one of the reasons why I took this out of a Kaggle set. So here's the leaderboard, right? You can see the score here, and again, you kind of have to understand Kaggle scoring, which I forget, to be honest. And let's see here, the data is, see, it's our exact same training set. So now you can participate in this Kaggle competition if you want. Discussions are great. How's the evaluation done? You can read on that. So different kinds of discussions here. Train, test, distribution shifts, advanced regression techniques, right? So what did they do to win this competition? I have a hard time remembering, because I haven't looked this. It's a pretty old competition. But I believe in the past, because they rerun this competition again, is getting into boosting. So so actually here, yeah. So damn, I'm telling you guys, there's a thing out there, and it's right here. So that's Grid Search CV. It allows you, maybe I shouldn't have showed you this. It allows you to run multiple combinations of hyperparameters. So I do want you to do them the own way yourself, and then run Grid Search CV. And what it allows you to do is Here it's running the number of estimators, and you can put an array there, run it for 100, 200, 300, max dead 100, 10, 20. And you can play around with this, put in as many you want, but don't do this until you understand how to do this, right? Play around with this yourself. It does take a little bit of time, but you got to get a feel for it. Yeah, it's so funny. I'm Googling this and I can't find it, and it's right here in my code notebook. I did actually write this code notebook, but I wrote it 2 years ago. Because like I said, machine learning, traditional machine learning doesn't change much. And I only give this kind of like once a year. So that's my excuse, and I'm sticking with it. So yeah, so grid search CV. So you're basically creating a grid, and then it's running through these things a bunch of different times. So I'm not going to go through that code. Oh, that code is not working. So where's it not working? Three folds candidates. So probably, again, it's probably old. No module. No. Okay, so give me the module name, because explaining the error, it'll give me the new module name, which I might have to do a pip install with. Okay, so because again, I don't want to look up the for God's sake, I don't think that's the right piece of code. But let me try it in case it is. So again, if you run this locally, you don't have to do this, but I'm going to do a pip install. I don't think that's the right solution. I think it's a clash between NumPy and something else, but we'll find out in 2 seconds. So bear with me. Okay, so I have a problem with cat boost. Okay. I'll talk about what cat boost is in a second. So this may not run. And see, the reason why it hasn't failed yet, because it's doing that multiple folds. It's running that model basically 243 times. See, fits means fitting the model. So it's actually running that model 243 times to find the optimal. And it actually is running. So while that's running, I have a results explainer here, and you will see that we're getting, R squared is still hasn't changed after 243 runs. It still hasn't changed, but that's a bit of a downer. But that's what you get from tuning. I talk about interpretability here a little bit, but I'm not going to go into it in too much detail. It's kind of a fun topic. Basically, I'm plotting out various features. One of the ones that's fairly popular, even though I don't use them a lot, are PDPs. And it shows the feature interaction between to influence prediction. So if we wanted to say, what's the interaction like? Because, when we talk about independent variables, are they really independent? And if they have too much influence over each other, then they might be bad here. So we kind of plot those out. That's running as well. So sorry, I'm doing my model fitting, so that's going to be running. So I think I'm kind of stuck until. So while that's running, let's talk about gradient boosting, which is, again, one of the most popular models out there. So gradient boosting is, and again, an ensemble technique. It can take some weak learners, weak results with high loss function, low accuracy, combine those together, and then it does, there's, if you remember gradient descent, gradient boosting, it tries to optimize the lowest loss function. So as you'd imagine, the number of boosting rounds we're going to do, we set that to some variable. This is a learning rate, number of threes, because it's kind of like a three technique. And again, I'm always setting my random state here. So I'm boosting this model. And again, I'm using the same metrics. I'm using R square, MSE, and R squared. And let me just show you the code here. So I'm still fitting the model, but now I'm using a boosting model, and that boosting model has these parameters set to it. And what else am I doing? I'm getting the mean squared error and the R scored here, pretty obvious. And I'm also plotting, just like I did with the decision tree, the random forest, give me the 10 most important features for XGBoost, which will be interesting to look at. And because I'm setting my random variable here, I already know the value because I ran this before, and it's got 91. And again, is the model overfitting or not? Not kind of going to go into that. But generally speaking, an R squared, a higher value is better. And we're able to explain 91% of this. I have to fix this cat boost. Cat boost is categorical boosting for categories. Remember, there's a lot of categories in that data set. So cat boost should be able to perform a little better. It's got some other, because you actually, with cat boost, you don't have to do that one hot encoding and a few other steps. It handles categorical variables automatically. And by the way, with XGBoost here, this is not optimal. I'm skipping a lot of steps that would have created better XGBoost. So kind of full disclosure, from what I recall, most of the winning methods here either used random forest or XGBoost or a derivation of one of the two. And some great insights here. This guy asking, should I replace these? And read it, right? So is there a discussion around that? No. Okay, that's not that useful. How do I get back here? So you want to play around here, but trust me, there are some really good discussions here. Different models. Oh yeah, so code is good too. So what you can do here is, oh yeah, I guess this is called the Ames data set. You can actually look here and see, can I say here? Yeah, this one here is 28 votes. So look for stuff that's got some good ratings on it. You can actually go here and look at their code, hopefully. And I can see here, what are they doing here? They're dropping some columns, align test. And actually, by looking at the library, I should be able to tell what are they using here. They're training it. They're using the standard scaler as we did. They're imputing some stuff. Be interesting to see how they're imputing it. Okay, that's a bit basic. That's not that interesting. Let me look at another model here. So there is a way to find the best models in here. Maybe this guy's doing something more interesting. Okay, yes, he's doing a lot. Well, he's using a linear regression model. Okay, so no, I don't think. Okay, here, XGBoost regressor. Okay, so decision tree, good. So this could be a good one to look at. Maybe there might be some interesting techniques here. That might be useful. Sorry, did I not share that? So yeah, go through some of these example code notebooks. And it'll kind of, if they did it right, they'll explain how, because see, they're doing it much more detail because we only have 2 hours here. See, they're looking at different the interdependencies between seeing if they can just combine these. No, actually, no. Is that one hot encoding? Yeah, it is. They're doing fence types and all that stuff. So they're kind of doing some encoding here. They're looking at overall quality. Your models, trying different techniques here. It's pretty fascinating. See how much more detailed this is. Sorry, I'm trying to get to the good stuff. Where's the good stuff? Where is the results? That's a better looking plot than mine, but still looks like a rug. Outlier analysis. Yeah, so see the way it's looking at quartile for outlier analysis. And here he's using a threshold, and see their threshold between first quartile 0.5 and 0.95. And yeah, zoning. Okay, come on. Where's the scoring? Correlational analysis. Okay. Okay, so that scoring is not a whole lot better than ours. What I want to do is find somebody who got a score around 94, 95. I should actually find that for you, but people are 29 is not bad. 26 is decent. 25, we got 17, so I think we did a better job, even though these guys did a lot more work. So I think our model result was slightly better. But I know there's model results out there that are much better. But this one is not it. But again, whoever wrote this notebook did a really good job of explaining it. So trust me, if you, yeah, see the features here, still overall quality. Overall, he's got another feature here, total basement square feet. His actually looks a little better, but I bet that's on boosting here. So let's look at what our results were. So did that run? Yes. Okay, so let's, so this is explainability. I don't quite have time to kind of explain what you're seeing there. But you can kind of go through. There's some interesting charts. You can kind of like at your own leisure, take a look at these. It's kind of a little bit of an advanced technique, but I do find it's kind of useful. See the way the pool area here is flat. So, well, actually, let me talk about it. So pool area flat, it's kind of telling me like pool area has nothing to do with house prices here. Living area, yes, kind of linear. This one here, what it's telling me is when the quality is really high, it has a big impact on. It's highly dependent on quality. When it's high quality, when it's low quality, kind of doesn't matter. Which overall, does that matter or not? Yeah, I guess it does. So that's why you see these kind of curves and S curves. So when it's flat and S curves like that, and you can see here with the different how overall quality, the prices kind of change depending on that. So yeah, so that's that. And then XG boost, as I said, we got a pretty good score here of 0.91. And see what our results here. We're saying the number of bats, number of garage cries. This to me looks pretty good. Like just knowing what I know about real estate, quality is not the main predictor. Like, and the number of full bats you have, whatever it is about it. Living area, I'm surprised living area is not higher. But this guy here, when he did here's his first, second floor. Yeah, I think that's good. Living area. So why is garage space so important in ours and it's not in his? Hard to know because it's down here. And his model is here, but his model results, maybe ours is overfitted, as Jonathan's suggesting, and maybe this is a better model. Maybe ours is overfitted to certain features. Maybe his is not because he's doing a lot more work than we are. So again, really, really good example. And this is why I love this example because I would say, I don't care if it takes you 2 days, 2 weeks, 2 months, 3 months, study these 3 notebooks I've given you, especially the last one, the last 2, and then go out there. Once you think you understand it, go out there and number one, compare it to other successful people in Kaggle, and then try it yourself. Go to Kaggle, start a profile, and don't be afraid. Yeah, sure, you might be copying code from my notebook, from everybody else's notebook, but who cares, right? You're just do yourself. And the great thing about Kaggle as well is you can be anonymous. You can choose to publish your results or keep them to yourself. So really, really good. And look, now you're getting away from, hey, I'm just doing a classroom exercise. You know, it's kind of almost the same as real world, right? And that's really useful. Okay, so. Yeah, so do you mean, sorry, I'm not sure what that question's about. Do you mean Seaborn, Matplotlib, or Yelphic? Yeah, so all of those are good libraries. Plotly, Seaborn, Matplotlib. So we're mostly using Matplotlib and Seaborn in this course, and Plotly is a great platform as well, and they have a big open source version. Another question here, garage spaces boost value, but beyond 3 cars, the impact plateau. Good. Someone's been writing this model, guide. Good stuff. Yeah, for this data set, right? For this data set. right? Different data set, different kind of houses. But I don't think we have number of cars. So yeah, so that's a good observation because that's a good observation because I don't know. Did I actually do that for garage? Yeah. Oh yeah, three here. Oh, you're talking about this? Yes. It doesn't matter after this one here. Yeah. Yeah. No predicted power when there's no garage. When it has between 1 and 2 and 3, and yeah, so these plots are kind of useful. I'm surprised why people in the Kaggle competitions don't use these more, because it kind of gives you an idea, better idea. But 81 columns, that's a lot of features, but maybe only 20 or 30 matter. Okay, so then this is XGBoost. What else do I have here? I have cat boost, but there's something wrong with my cat boost. Is there? Did cat boost work? So cat boost is categorical boosting. So yeah, I got to go fix this. I think there's a dependency error here between that and so I'm installing these libraries. I don't know why it's working. So I'll go fix that. And then there's a K nearest neighbor one here. KNN is another decent model. But I'm just, again, the results are not that great. I'm just giving you two from completeness. Good one to hyperparameter tune. So just so you know it, but it's not going to win this competition for sure. All right. Yeah, and there's another little piece you can read there. So I'm going to wrap this up. Thank you very much. Bye-bye.